Let us try to understand what is bending stress and what is shear stress. You just imagine a simply supported beam subjected to a point load at midspan of the beam. I want to show you a model. Look at this picture. This beam consists of some layer. I have given different color to different layer to understand it very well. Those layers are free to each other. That means there is no any kind of friction between two adjacent layers. This is the cross section you can see before the application of load, and this cross section makes an angle 90 degree with the longitudinal axis of this beam. Now we are applying the load gradually. This is the cross section that you can see after the application of load. If you draw a tangent over here, then you can see the angle between the cross section and the tangent is less than 90 degree. That means after bending, cross section is not perpendicular or normal with the neutral axis. Why this is happening? Because all layers are independent. The longitudinal length of each layer after bending is same for all layers. They bend about their own individual longitudinal axis. So each and every layer get compressed and extend at top and bottom. There is no common surface between two adjacent layers. Therefore, the bottom surface of the upper layer will slide over the top surface of the bottom layer. Now I want to show you another model. Now suppose all layers are glued along the contact surface so that they become a single solid beam. Now you can see the cross section of the beam perpendicular with the longitudinal axis before the application of load. When the load is applied in transverse direction of the beam bends. Now you can see if I draw a tangent over here, the cross section is maintaining the angle with the axis of the beam. That means after bending, the angle is perfectly 90 degree. You can also see that the longitudinal fiber above the neutral axis get shortened and below the neutral axis get elongated. Now it will be clear to you if I superimpose those two models. The white layer indicates the individual layer. The topmost fiber of the beam get compressed because the lower layer is trying to keep the end of the upper layer with its own end, as they are not acting individually. We can say that virtually a compressive load is applying along the longitudinal axis of this particular layer. You can see the amount of strain here. So total amount of strain will be 2 multiplied by this distance, because both ends will shorten with same magnitude. Now you can calculate the strain by the formula, that is change in length divided by original length. The direction of strain is along the longitudinal axis of this particular layer. That means this is a longitudinal strain. If it is longitudinal strain, then we can say that a longitudinal stress must be there. That means the direction of stress is normal or perpendicular to the cross section of this layer. Now for the lower layer, you can see the amount of strain is less than the previous one. So we can say that the produced stress will be less than the previous one. And for the next layer, the same theory will be applied. If you indicate the direction of compression toward left, then the direction of tension will be toward right. The maximum tensile stress will be developed at the bottommost fiber because the strain developed at the bottommost fiber is maximum. If we connect all those points, we can see the stress diagram. Due to strain in the fiber along the longitudinal direction, the stress are induced. Since this happens due to bending, this is called bending stress. Now take a look how this bending stress is gradually increasing. Now, if you draw shear force diagram, shear force will be positive at the left hand side of this point load. You just assume two cross section and see what is happening. One upward tangential force will create due to the reaction. To nullify this upward tangential force at the right side of the left part, there is a downward tangential force at the left side of the middle part. So those two will make a positive shear force. And to nullify this downward force, tangential force, there is an upward tangential force at the right side of the middle part. Again, to nullify this upward tangential force, a downward tangential force created by the external load will act at the left side of the right part. Now consider a particular layer. You can see those two tangential force is nothing but a couple of force. And this couple of force is creating an anti-clockwise moment. But the condition is that our structure should be kept in equilibrium position. To keep this body in equilibrium position, a clockwise moment should be there. That means a horizontal shear stress and a vertical shear stress is exactly in same magnitude and in with opposite direction. Please keep in mind when we calculate the shear stress and draw the shear stress diagram for a particular section, we are actually calculating the horizontal shear stress. Depend upon the distance of this layer from the neutral axis. As we know that both are in same magnitude, we can say this is also vertical shear stress. At the end, I want to say you the model that I have shown you is actually wrong. Yes, it is not correct. Next day, I shall tell you what is the actual model and why this model is wrong. Thank you.